Hello everyone, welcome to Science Sphere. Today, I'm going to share with you the mystery of antimatter. Antimatter, a concept that sounds like it belongs in science fiction, is very much a reality in our universe. It's one of the most enigmatic and fascinating subjects in modern physics, challenging our understanding of the cosmos and the fundamental laws that govern it. At its core, antimatter is the opposite of ordinary matter, with the same mass but opposite charge and other properties. The story of antimatter begins in 1928 when British physicist Paul Dirac predicted its existence through his equations. His mathematical model, which combined quantum mechanics and special relativity, suggested that for every particle, there should be a corresponding antiparticle. This groundbreaking theory was confirmed just 4 years later when Carl Anderson discovered the positron, the antimatter counterpart of the electron. Since then, scientists have created and observed antiprotons, antineutrons, and even entire antiatoms. In particle accelerators around the world, antimatter is routinely produced in small quantities. However, creating and storing antimatter is an incredibly challenging task. When matter and antimatter come into contact, they annihilate each other in a burst of pure energy, as described by Einstein's famous equation E equals mc squared. This property makes antimatter both fascinating and potentially useful, but also extraordinarily difficult to study. One of the greatest mysteries surrounding antimatter is its apparent scarcity in our universe. The Big Bang Theory suggests that equal amounts of matter and antimatter should have been created at the birth of the universe. Yet, the observable universe is composed almost entirely of matter. This asymmetry between matter and antimatter is one of the most profound puzzles in physics and cosmology. Scientists are working tirelessly to understand what mechanism could have led to this imbalance, as it's crucial to our understanding of why the universe exists as we know it. Research into antimatter has practical applications beyond pure science. In medicine, positron emission tomography, PET scans use antimatter to create detailed images of the body. When positrons from a radioactive tracer annihilate with electrons in the body, they produce gamma rays that can be detected and used to create images. This technology has revolutionized medical imaging, particularly in cancer diagnosis and brain research. The potential of antimatter as an energy source has also captured the imagination of scientists and the public alike. The energy released when matter and antimatter annihilate is enormous, far more efficient than nuclear fission or fusion. A single gram of antimatter annihilating with a gram of matter would produce an explosion equivalent to a 43 kiloton nuclear bomb. However, the challenges of producing and storing significant quantities of antimatter make this application purely theoretical for now. In the realm of fundamental physics, antimatter serves as a powerful tool for testing our understanding of the universe. The standard model of particle physics predicts that matter and antimatter should behave in nearly identical ways. Any differences observed between them could point to new physics beyond our current theories. Experiments at facilities like CERN are probing these questions, comparing the properties of hydrogen and antihydrogen atoms with unprecedented precision. The search for antimatter in space is another exciting frontier. Some scientists theorize that there might be entire galaxies or regions of the universe composed of antimatter. Detecting such antimatter structures would be a monumental discovery, potentially reshaping our understanding of the cosmos. However, finding evidence of large-scale antimatter in the universe is extremely challenging, as the boundaries between matter and antimatter regions would produce intense gamma radiation that we haven't observed. The mystery of antimatter extends into the realm of cosmology and the nature of the universe itself. Some theories suggest that the matter-antimatter asymmetry might be related to the existence of dark matter or dark energy, the unknown substances that make up the majority of the universe's mass and energy. Understanding antimatter could be key to unraveling these cosmic mysteries and potentially discovering new fundamental forces or particles. As we continue to explore the nature of antimatter, we push the boundaries of our scientific knowledge and technological capabilities. From tabletop experiments to massive particle accelerators, from theoretical physics to practical applications in medicine, the study of antimatter represents one of the most exciting and challenging frontiers in science. It reminds us that the universe is far stranger and more complex than we often imagine, and that there is still so much to discover about the fundamental nature of reality. Thank you for watching. If you enjoyed my video, remember to like, subscribe, and share with your friends. See you next time.